No need, sir. No need. The first slide up here, sir. No problem.
Okay. College sir, ready?
Okay.
இது எடுத்து ஒரு கிட்டத்தட்ட எவ்வளவு இயர்ஸ் ஆயிருக்கும் 9 இயர்ஸ்
சார் நியூட்ரல் கொடுத்துருங்க.
ஓகே சார்.
பாலச்சந்திரன் நியூட்ரல் கொடுத்துருங்க.
9 இயர்ஸ் இருக்கும்.
நியூட்ரல் கொடுத்துட்டு பாலச்சந்திரன் சாருக்கும் சாருக்கு மட்டும் ஹெல்ப் பண்ணுங்க சார்.
அதெல்லாம் உங்களுக்கு லேப்டாப் டேப்ல பாத்தீங்க. டேப்ல ஒன்னு தான் நல்ல ரெண்டு.
One second, கொடுத்துட்டேன் பட்
ஓகே பாலச்சந்திரன் சார் ரெடியா?
ஓகே சார். ஓகே
பாலச்சந்திரன் ரெடி
சார்?
One second. Okay, so I unmuted Balachandar and guest.
Okay.
Sanmasudha sir.
Dhandapani sir, unmute பண்ணிக்கீங்க சார். Dhandapani sir, kindly unmute yourself.
Sir.
Okay.
Audible sir, audible.
Just stop sharing பண்ணிக்கீங்க சார். First நம்ம வீடியோ காமிச்சிட்டு அதுக்கு அப்புறம் we can start the Just on your video sir. Yeah, video is visible. Right. Thank you sir. Yes, thank you participant. Balachandar, please hand over the section.
Okay, thank you, sir.
Video on.
Happy afternoon to everyone. I welcome to this third session of the AICTE sponsored STTP program. For this session, I heartily welcome our eminent speaker, Dr.S.Dhandapani sir. Professor has completed UG in Madras University, PG in Annamalai University, and Ph.D. in SCS BME University, Faculty of Engineering, Technology, Kanchipuram. He has more than 19 years in teaching experience and 5 years industrial experience, and also served under UNDP program at Ethiopia, East African country, for 3 years at Adama University and Baghdad University. He has published more than 6 papers in reputed journals and conferences. His area of research is machining over EDM on nanocomposite materials. He is a life member of ISTE and also received Best Lecturer Award at Affiliated College of Anna University. Currently working as professor at Rajalakshmi Engineering College, Tandalam, Chennai. I welcome you, sir.
Thank you.
Kindly hand over the session to Professor Dr.S.Dhandapani sir.
Okay, sir. So thank you, sir. Thank you for the HOD and introductory speaker. So I am here. First, good afternoon to one and all and the participants. And I am here to deliver this section, the topic under the topic of microstructure evaluation of smart material. So let us see from the microstructure and then smart material. First, this content microstructure and which is dependent on the phase changing crystal and defects, and then microscope, how the imaging and resolution, and then measurement of microscope and general types of microscope, namely optical microscope, XRD, SEM and AFM, TEM, that is scanning electron microscope, atomic force, and transmission emission microscope, and smart materials. Then the smart material, and then transformation, how the mechanism of smart material, properties and components of smart material, classification of smart material, and application in real time. So first introduction, the microstructure. See the microstructure, how it is, the elements, namely the crystal and the phase changes, the phase changing, how the crystal unit cell, the basic elements are there. In that, based on that, first, it is a very small scale structure of a material defined as the structure of prepared surface material as revealed by an optical microscope above 25 magnification scale. The microstructure of the material, namely the metals, polymers, ceramics, composites, can strongly influence physical properties, by meaning that by the temperature, pressure, or external factors will increase this strength, toughness, ductility, hardness, corrosion resistance, and high-low temperature behavior like that. So these properties in turn govern the application of this material in industry. So the change in microstructure will vary the properties. So what is before that? What is the microstructure? For that, the basic elements, namely unit cell, atoms, crystal structure. Already we know all. But even though just recalling, the term crystal structure is used to describe the average position of atoms within the unit cell, and is completely specified by the lattice types. So the crystal structure is described by the atoms and within the unit cell. So unit cell is a combination of the atoms. Atoms, we know that, and then and specified with the lattice and the fractional coordinates of the atoms. Determine the X-ray diffraction. X-ray diffraction is the microscopic principles. We will see that. And the fractional coordinates indicating that, for example, the unit cell and the lattice cell, see that the simple cubic body centers are FCC phase centers per atom. Totally we are seeing number of atoms, but it is a fractional coefficient, 8 atoms into 1/8. That is fractional. That is the fractional coordinates of the atom. So totally one atom only. So we know that already, but based on that, the crystal structure and the unit cell atoms and this is related with the microstructure, how it is forming. So this crystal structure describes appearance of the material on the atomic Armstrong length scale. So crystal structure is described in this unit scale. But finally, what is the microstructure is used to describe appearance of the material and the nanometer and centimeter scale length. So this we can say finally the arrangement of phases and defects within the material. So microstructure depend on the two parameters, namely phases and defects. So what is phase? Phase changes. We know that this solid phase and liquid phase and gas. See, when the solid, the energy is added and it will, that is by means of melting, it comes liquid, and further adding, it will go for evaporation and gas state. So the energy is added, but again, the energy is extracted. So heat, and then thereby condensation, and again back to vacuum to liquid, again freezing it back to solid. So the energy is mainly involving in this, and thereby phase is changing. So that is a phase. Phase is taken to be any part of material with a distinct crystal structure and the chemical composition. Different phases in material are from one another, that is by distinct boundaries. So crystal structure, that is the overall combination of unit cell and atoms it will form. So we know that these examples, iron and vanadium, niobium, chromium are for BCC, like that FCC, etc. So just recalling the things. As I told, the phase and defects are main reason for microstructure formation. So defects is taken to mean any disruption to the perfect periodicity of the crystal structure. So the disturbance by the external parameter, as I already told, the temperature and pressure. So in what way this is classified by point defects, line defects, and planar defects and volume. That is 0-dimensional, 1-dimensional, 2-dimensional, and 3-dimensional, based on the directions x direction, y, xy, and xyz direction. So what is point defects? That's only atom missing in your irregular plane lattice. That is point defects. Then line defects, that is linear defects. Group of atom in a regular position is disoriented, mismatch. That is screw and edge dislocation. We are not going to deep in these details, but just what is point defects, line defects, planar defects. There, that is interfaces between homogeneous regions of the materials. There is formation of grain boundaries. Volume, it is these overall extended defects. Porous cracks are comes under volume defects. So we have come across the phase and defects with these two parameter. These are the example for the planar. Just recalling the defects, planar defects and point defects examples. So now the microstructure, how it is forming. it is almost always generated when a material undergoes a phase transformation. So we know that what is phase, how it is transformed, brought by changing temperature or pressure. So what is solidification? So the process of transformation of substance from liquid to solid state in which the crystal lattice forms a crystal appear. So transformation from liquid to solid state. So that is the way of shrinkage, volume or volume contraction. That is, so actual solidification means in the pure metal and eutectic alloys takes place at constant temperature, meaning that in the constant temperature the phases will change. Pure metal eutectic alloys means that is below melting point, it is going to change. So it's at constant temperature itself, there is chances to changes of phase. In solid solution, alloys proceed over a temperature range. In the solid solution, there is a range of temperature. In between that, the transition will take place. So the transition or solidification or crystallization occurring in two stages. One is nucleation, grind, that is growth. But this nucleation is very small formation of crystal. When you grow under a thermal and like crystallographic condition existing during solidification, grain growth stops and complete and solidification is completed. See that in this diagram, the melting of solid and increasing energy, and thereby it comes liquids. And further the energy is decreasing and it back to solid. So energy is main involvement. Energy in the terms here, the temperature, pressure, like that external parameter, and it will act the elements of the microstructure and formation of, there is two important, one is nucleation and grain growth. Again, further explanation on this, during solidification the liquid changes into solid during cooling. So the liquid is changed to solid during cooling time. So the energy of the liquid is less than that of the solid above the melting point, hence liquid is stable. So above the melting point, liquid is stable because the energy is less comparatively solid. Similarly, below the melting point, the energy of liquid becomes more than that of solid. Hence, below the melting point, the solid becomes more stable than the. So above the melting point, there is a liquid is stable. Below the melting point, solid is stable based on the energy concept. So finally, liquid converted to solid during cooling. So transformation of liquid into solid below melting point is known as solidification. So here in this diagram, time temperature diagram, liquid phase is there, and then is the eutectic, the pure metal phase, that's a constant temperature, and then further the solid phase starts. So here this diagram, this nucleation growth, next nucleation and grain growth. How this first diagram, nucleation of crystal growth, and then irregular grains forms as crystal growth, and then third one, grain boundaries as seen in the microscope. See how the crystal, this one, so, this solidification temperature atom from this liquid such as molten metal begin to bound together and start to form crystal. See that it is the nucleus formation, and further addition of number of nucleus, it will form a new crystal. So the movement of crystal begins to grow known as a nucleus. At that point where it occurs is the nucleation point. And then when the metal begins to solidify, multiple crystal begin to grow in the liquid. So multiple crystal will grow like the second stage, crystal growth stage. And then final sizes, finally, when the final sizes of the individual crystal depend on the number of nucleation points. So finally, it will enlarge at one limit. The impinging, the area will be bounded, and in all each other number of crystal will impinging each other, and it will form a boundary line that is called the grain boundary. That is the final microstructure shape will form. This is the mechanism behind the formation of microstructure, nucleation, and grain growth. So one polymeric material, for example, just a layout of the understanding purpose only, it is shown. That is, for example, if you take any solid polymer intermetallic molecules like the chain shape, and when you heat it and it is collapsed, it is number of things is reduced to 4 number. It is, if it is here for 6 number, it is 4, and further heating, so energy is added, thereby final aggregates with the swollen shell, and further heating it becomes full solid state. So in this process, fully heating is taken. Further cooling, the swollen aggregates separation will take place. Further separation like that. Finally, further cooling, it comes back to final coiled chains. So this is mechanic heating and cooling is the main impact of the microstructure formation. This is phase transformation. So the basic principle of microstructure, this is just recalling. This is not fully we are not explaining, but the structure, just a sample of structure, alpha grains, alpha, beta, gamma. We know that already in metallurgy we studied ferrite, martensite, the sample shapes. Ferrite has some, each individual phases has their own characteristics, some soft and ductile, while perlite is hard. Ferrite is harder than the austenite. Perlite is a microstructure which contains both ferrite and some. So like that, the martens is originally named for very hard, brittle. Austenite in the face of FCC structure which exists above 720. So like that, bayonet, lead, lot of things are there, but just recalling the phases. So examination, microstructure examination by the instruments. That is, examination, microstructure examination generally performed using optical or scanning electron microscope to magnify features of the material under analysis. The amount of size of these features can be measured and quantified and compared with the acceptance. So it is measurements, how this microstructure is measured by optical microscope, scanning electron, transmission electron microscope, atomic force microscope, scanning tunneling microscope, scanning probe microscope. Just we will see the most of the things which are in usage. We will see these 4 things one by one. Just the basic principle is the imaging resolution. That is a diffraction concept. Diffraction is the concept that is explained using Huygens principles, and it's defined as the bending of wave around the edges of an opening or obstacle. Anything that the phenomena is the wave. That by applying this theory to light passing through a slit, we can what this explains means. It is a element, that is a object diffracting, grading. It has this slit, and when the light of electrons is passed through this, and this is the split through this slit, when it's entire, it is touching the edges of this object, and thereby, as per the Huygens principle, the light electrons will bend, whether plus theta or minus theta. Based on it, bending will take place, and thereby bending, it will go a certain distance, and obstacles, that is a lens, electromagnetic lens, are there, and again further change in angle, and certain, depending upon the intensity of this certain place, it is going to be contracted. That is diffraction pattern, and further magnification will take place. So finally, the magnified images we can able to obtain. So this basic principle of diffraction, that is the distance from this object to the lens obstacle, u distance, and the v distance, the outlet, and the f distance is focal distance. So these things, mathematical formula they framed, that is Abbe theory of imaging using all diffracted spots. So this can be satisfied if this the image is formed when the equation 1 by u, 1 by v, that is focal f, is satisfied. F is the focal length of the lens, and d sin theta n lambda, that is the diffraction formula. The radiation with the wavelength lambda is the incident of the object. Each slit is grading scatters the radiation in variety of directions. So when each slit has that is each we have seen that it is each that is diffracted, each slit diffracted, and radiation scattered in given direction collected in the lens, and the distance at distance u from the object, and focus in the point and back to the focal point, and f located in distance f from this. So they are explaining the same. So this d theta sin n theta, that is deeply explained in the Brock's law. Brock's law we will see in the next in the XRD. XRD we will see that. This is the basic of the diffraction principle. For example, of the magnification of the same solid solution containing hematite and ilmenite, that is the iron oxide and iron tite. It is mixed with how this this microstructure from where it came means. Let us see this sample of mineral titohematite, a solid solution containing hematite and limetite. as this mineral cooled very slowly over a period of 1 billion years of pellets of limited habitat. It's all see this mineral cooled by cooling. It is after 1 billion years like a rock, and it was formed as a two platelets. One is limited and another is emitted, and this is caused by the reduction in the distance over the which atoms can diffuse as the temperature decrease. Plates formed high temperature, meaning the what they are thick and widely spaced, whereas those formed low temperature, what they are telling, during cooling, the atom is forming very distance due to the temperature high. If the temperature is high, the thickness plates is higher, and when the temperature is low, the plates thickness is lower. So based on that, it was formed for the that base, and that the structure explained, the magnification purpose it was explained. Low magnification, first word, low magnification, scanning electron microscope, this one SEM analysis, images of two-phase intergrowth of etched limitite, hematite. This is the platelets. Dark patches of show where hematite lamellae have been preferentially dissolved out of limited host, meaning that this limitite is the main over which hematite is dissolved. So one is solution solvent, like that hematite is dissolved. These black color lines are hematite. The white color are limitite. So hematite lamellae have been preferably dissolved out of. So white colors are the black color lines are hematite is dissolved. So at this magnification scale, low magnification, it seems like this. Same picture, if you go for 500x higher medium magnification, this single black line seems to be, there is already, this is single black line, but we are seeing number of black lines, that is this dissolution of hematite. But here, same single line, due to magnification, further there is a little bit of lametite is presence, not 100% dissolution has taken place. And after magnification only we can found this. So again, further magnification, high magnification, the same is seems to be by electron microscope image, the hematite plates in an limited host. Note that the length of the scale platelets decreases from left to right. The size is meaning that you are seeing some light white color lines, and this same length, if you see this place, very small. So that is a 1 to 2 nanometer unit cell. So such a way, high magnification seems to be like this. So the magnification purpose in this sample is shown how the microstructure magnification is important, and based on that the types of microscope is classified. So measurement, how we can take, there is general measurements concept. One is depth measurement and surface measurement. Depth measurements, the first group include measurement of depth for depth of decarburization, depth of surface hardening and coating. So surface measurement, surface hardness treatment, how much we already studied the surface treatment. We cannot do to ordinary industries. Costly material cannot be purchased, so ordinary material has to be heat treated, and further it is to be hardness to be increased. So surface only it is to be heat treated. That the surface heat treatment, we have to measurement how much depth measurement, how much penetration of hardness. So these measurements are made at a specific location at surface, and they will be subject to considerable variation. So at a particular point they will find out how much the depth is hardness is entered. But second group of measurements belongs to the field of referred to as stereology. Stereology means that is surface 2D. This body of measurement describes the relationship between the measurement made a two-dimensional plane of polish and the three-dimensional. See, it belongs to 2D and 3D. To surface XY, and also it is for the 3D image also possible in the surface. So two types of measurements. In the second one, stereology measurement surface. For example, it is shown how within a box, they will frame a box, and within a box, how many grains are there. That is This micrograph illustrates grain counting procedure. How many grains are inside some designed structure. Planimetric method is used to using as a rectangular area. That is called a planimetric method. I will say what is the purpose. Another method is also there. We will say what is that. And NA, that is a numerical aperture. Numerical aperture is based upon the 53 grains completely inside the rectangle. So 53 number of grains are fully presented inside, and 1/2 of 43 grains intersecting straightly. So within the boundary, 53 grains are fully covered. Remaining 43 grains are partially covered, partially outside. So total number of grains presents inside to be calculated accordingly. So they will count half of the grains of 43 divided by 2, and that has to be added with the 53, like that. And also at the corner, one full corner grain contribution of 4 grains intersecting corner. So based on that fraction value is added with the full grains. Total grains will be calculated. There is a formula is there. Let us see that next. This is one sample how the grain. So there is a International Society of Stereology and Image Analysis there. That is the purpose is the society whose purpose is to encourage the development of knowledge and stereology. The image analysis is a wide range of disciplines. It was found stereology, that is 3-dimensional interception of 2D dimensional cross sections of the materials and the tissues. That is ISSIA is a standard which is stereology measuring laboratory purpose. This table shows standard notations. This we have a number of points on the elements, point fraction, and the length of the linear elements, test line length. So we have seen a previous diagram. Based on that, depending on the diagram, there is a lot of things are there. Sample I have shown number of points per test volume, number of like this. This is a notation table. Like that, lot of tables are there. Based on the table, formula table is there, and they will find the grain size, grain growth, and all these. For 1 or 2 samples are here. This one say we are studied. You might be seeing various SEM analysis, TEM analysis. It is magnification 10 by 10, 5 by 10, 5 by 5, like that. And that meaning is horizontal line 10 and vertical line 10. Within this, it is divided. Within how many grains are fall. That is the synthetic microstructure of uniformly shaped, identical size spherical particles in a matrix phase. So here test area 12,100. How the area is calculated means the length, total length 110 mm horizontal, 110 mm 110 vertical. So 110 into 110 12,100. This is the way they will calculate. In which 10 horizontal, 10 vertical. This is one way of calculation. Another one example of grain size measurement by planimetric method, that is micrograph 100x of an austenite manganese steel that was solution annealed. So they are making is treatment, annealing and aging to grain boundaries to fine perlite. They are changing austenite to perlite, and in that how they after changing they are calculating how the grain size before austenite, what is the size of the grain, after austenite perlite formation, what is the size. The difference only it will based on that the hardness or something they will found out from this. So for that the circle diameter is given 79, and for this area is given, and the count is made to determine number of grains completely within a circle. So within a circle the number of completely grains are 44. The number intersecting circle 25 grains boundaries are intersecting, as already told that. And the number of grains, how they are calculating the planimetric multiplier. This is a method. Planimetric is a method. For that 100x, we are making it to 100x magnification scale. For that multiplication factor is 2. There is standard table. They will take the value. The number of grains per square millimeter is 1. So per square millimeter there is a 1 grains into multiplication factor from the table they will take. What is the size you are taking? Correspondingly, we will check in the table. For 100x, multiplication factor is 2. Like that, they will vary. For 500x, it will vary. 600 vary. So for 100x, it is 2. So they are multiplying by 2. Then, and this total number of grains. So they told that inside full grain is 44, 25 grain is partially is there. So 44 plus 25 by 2. So total value 113. And ASTM's grain size for 113, there is a formula is there. Based on the formula, they will use logarithmic scale and minus, there is standard formula minus 2.5, 3.22 is the formula. And we will include this 113 only, what is the value obtained, and we will substitute this and we will have 3.87. And they will make it a round of 3.9 and 4. So the grain size is 3.9 or 4. So like this, one sample only, lot of things are there, but just sample we have seen. As I told that the plane metric and intercept method is, plane metric method is for equiaxis. Intercept method what is equiaxis, non-equiaxis means, we have seen this previously slide, the grain growth. Initially the crystal structure form and equal axis like symmetrical, unsymmetrical. The growth of crystal structure is all the crystal structure are equal axis size, shape, same shape, and non-irregular shape, that is a uniform, non-heterogeneous like that. So non-equal axial grain structure require measurement on the three principles, because non-equal axis is if equal axis means both symmetrical, so it is easy. But this non-equals and non-symmetrical. So three planar principle: longitudinal, planar, and tangential. The example of this grain size measurements using the intercept method. There is a three concentric circles have diameter different. This diameter is given. Total line length, total diameter 11, and total line length of measurements, and 500 maximum 500 they are using 500 magnification scale. One they taking line length is 1 mm. The count of number of grain boundary intersections several. See, they are approximately they are doing revealed 60 grain boundaries intersection, 7 triple. So there is a 60 grain boundaries, 7 triple line junction. Triple line junction means 3 grains will junction at your point. That is 7. So they are doing 7 into 1.5. They are taking 1.5 for 3, because full means 1, half means 0.5, 3 means 1.5. So they are taking 7, 3.5 plus 60, it is 70 point. And they are bringing 70.2, and they are similar way they will check in the formula. There is a formula 1 by PL, they are dividing 0.142. AST is a formula using, they are founding it to 8.99. 9 is the grains. So a lot of the things are there. Just to go through your samples, we are seeing this the intercept method and plane metric method of grain size measurements. So let us see one by one. Just optical microscope, scanning electron transmission. Optical microscope is light microscope. It's a type of microscope that commonly uses visible light and a system of lenses to generate magnified lights. So the same principle as already we have seen the X-ray diffraction. The object is placed on a stage and may be directly viewed through the 1 or 2 eyepieces. So here best resolution of the microscope, optical microscope is 0.2 microns. This is 200 nanometer. So maximum magnification here possibility is 100x, because they limited the 1000x. 1000 is beyond 1000x we cannot. This function is same concept of diffraction function. It is functioning under this diffraction principles. So, but optical microscope, the specimen has to be prepared small size. We cannot keep it on the table, measuring table. For that, there is a procedure is there. A mounting machine and then a polishing machine. How the mounting is small. These are the samples. The sample we can hold by finger. For that, we need some holder. Because this small pieces is embedded over the holder. This holder is made from a lot of chemicals, methods are there. Sample specimen, the most specimens mounted, and that name is called slides. And there is a flat rectangular of thin glass also there. The specimen is placed on the glass, and a cover slip. There is a holder name, cover slip is placed over the specimen. This allows the slide to easily inserted, removed. So with this holding purpose, this black color is the holder. That is, they are saying slides and cover slip. And then etching is to cleaning the surface, etching chemical agent. Surface specimen is a tipped and etching agent, and rubbing, cotton stopped, and electrolytic etching. Etching is for cleaning purpose. For sample I gave you, for silicon, if it's a metal is silicon, we have to use these types of etchings, nitric acid plus hydrofluoric acid, potassium hydroxide, like that. If it is aluminum, separate, like that. Depending on the metal, the etching agent will vary. So this is the how they are mounting means this mounting preparation. This specimen is prepared using this mounting machine. This small sample and it is mounted. Now it becomes to hold purpose. Now with the holding we can polish it and then we will keep it in the optical microscope this place, the sample specimens place. We can easily keep it. Then X-ray diffraction, XRD, that is X-rays are generated a cathode ray tube. Previously, we have light rays, electrons, is X-rays filtered to produce monochromatic radiation, collimated concert, and directed towards this sample. So this is the X-rays, as I already told, it is functioning under Brock's law. Brock's law in the physics, you might be studied this. When the 2 theta lamp is when it is X-rays, incident rays are focused on molecules. And the distance intermolecular spaces is d, and theta angle 2 theta sine theta diffracted rays, and it will satisfy formula n number of molecules, lambda the wavelength, incidence wavelength, and 2d is the space theta is the diffracted angle. So it will satisfy this Brock's law. It is impinging over this and diffracted to X-ray rays. So using this X-ray, we can X-ray diffraction, so we can able to identify crystalline phases and orientation, and then we can distinguish between crystalline and amorphous. That is in crystalline material and amorphous non-crystalline material. Determination of structure of crystalline material. We can determine the structure and also determination of electron distribution within atom throughout the unit cells. So like this, to measure the thickness of thin films and multi-layers, determination of orientation of single crystal. Like that, determination of structure and polygrain materials. So we will see we will measure these types of parameter using this X-ray XRD. This is sample when I used to do in the research work that was taken. That is Joint Committee of Powder Diffraction Standard. There is a standard is there that will make this confirmation of the material. Same Brock's law formula. These are the possibility of measurements. Say this is sample table. JP, I told JCP the standard sample. I used the boron carbide. So boron carbide table is there. If the angle is available, for example, this is magnesium XRD, but I used boron carbide that is not shown. For example, the magnesium carbide peak angle will be there. There the peak magnesium is present. Corresponding angle we have to go and check. Corresponding angle is here. For example, for peak 34 and 86 available in my XRD graph. So 34 is here. So nearly 35 is present. 86 is present. So it is confirming that your boron carbide is present in the microstructure. Like that confirmations for the JP series table is using. So the same, what I told this for this purpose, it is interlinked. These two only here, but I have it is boron carbide I gave, but it is given in the magnesium graph. Same magnesium also there is another table is there. I have not taken here. So magnesium it was present 1.1%, 6%, 10% ratio, 3 samples and 3 graphs are there, and these are Miller indices. That is internal crystallographic 112, 20, 200. Miller indices. It automatically both will be displayed in the outlet of the answer as a printout in the digital form in the XRD machine. So scanning electron microscope, I think you might be studied previous also. The scanning in electron purpose. The scanning is 2D purpose. Here the incident waves are focused and backscattered electrons are forming, and it will atoms, how the atoms are present upon peaks and valleys can be possible to the microstructure details are magnification and displayed in the magnifications screen. So the scanning electron microscope will allow you surfaces 5 to 3000 magnification up to the high quality, high depth of field. Also, it is used to failure analysis, contaminant analysis, general microanalysis. These are the advantage. And EDS, the energy dispersive energy, because this energy is the main factor of microscope success. So energy software is added with the SEM analysis. SEM analysis will result microscope structure will give, along with that energy dissipation. Energy means that the presence of how much intensity of the phases, presence and confirmation, that chemical composition details also added with this. That is meaning that XRD, EDI, EDAX and SEM is added. So this is SEM definition. We already studied the electrons interact with atoms in sample, producing various signals that contain information about the surface topography and composition. So this is my main purpose is topography, surface topography and composition of the sample. AFM is, that is AFM, the difference between SEM and AFM is this is 3D, mostly 3D. Cantilever is very inside, there is a cantilever with a very sharp tip to scan the sample surface. As the tip approaches surface, the close range, and attractive force between the surface and the tip cause the cantilever to deflect, meaning that here the SEM analysis only rays are impinging on the surface of the microstructure. Here AFM, there is a one needle like cantilever, it is going to touch the surface because of up and down valleys and depth are there, and it will deflection will takes place. That cantilever deflection is focused by a laser lace based on the so comparatively SEM AFM 3D model can be possible, high quality available atomic force. TEM also somehow nanoscale level. SEM also possible. Some of the things TEM highly magnified. So it is also one of the things. We will try SEM TEM. If you already studied, we will go fastly this SEM explanation, TEM explanation. So electron microscope are scientific instruments that are used as a beam, highly energetic electron to examine the objects on a very fine scale. This examination can yield information about the topography, morphology, and same things. There is two types electrons: TEM analysis for inner structure, SEM analysis for the surface object. So this is the SEM working principle. That is the the input electron gun and condenser light it is bringing. Condenser lens controls the amount of electrons traveling, electrons controlling, and the object lens focus beam to spot the sample. And further, deflection coil helps to deflect the electron. So the deflection coil will deflect the electron, and some electron detector can attract the secondary electrons. Secondary electrons, again, because of deflection, there is formation of secondary electron, and it will fall on the sample, and the additional sensor, and the display will be the vacuum. Inside the vacuum only this is kept. These are the principle how the backscattered electrons are coming out. So only rays are coming, and this impinge, the backscatter rays are going out. That mechanism is shown. Sample preparation, like that SEM also we have to prepare sample. There is a sample preparation, and in this they have to keep the sample, and it will prepare because we are using device called a spooter coater. Using this device, sample is placed small chamber that is at a vacuum. This vacuum, cold foil, gold coating is needed. For that, gold foil is placed inside the instrument. They will keep through the argon gas. They will make a slight deposit on the surface of the specimen. Here, specimen. This is a spider coated gold. That is a specimen like this. Argon gas and electric field cause an electron to be removed from the argon and making the atoms positive charge. So already gold is gold foil. There is a negative charge. So that by application of argon gas, the gold from the gold foil, the deposition of the surface of the specimen will be happen inside the machine, and after we will take it out. The argon ion knock the gold, and the final output will be. If you keep the specimen and the cold foil and apply the argon gas, everything will be happen, and final output will be the gold coated the specimen, and that only kept inside the SEM. That is how this is where they are preparing. Advantage It gives a detailed 3D proper image, and instruments very fast. Modern SEM allow the generation of the data in digital form. SEM samples require many preparation. So disadvantage is also expensive, large spatial training is required. Some preparation of samples can result in air graph. SEMs are limited to solid. SEMs carry small risk of radiation exposure. So it is there is some exposure is there. Sample TEM analysis. TEM analysis, there is also similar fixation, rinsing, straining, dehydration, embedding in rising, like that procedure, fixing with chemical products. Fixed with the chemical. The sample is very small. Mostly TEM analysis, we should not, the specimen should not contain ion free elements only. It is used. The rinsing is treated with heavy metal components, rinsing and straining, and then dehydration, washing with increasing ethanol, fully chemical treatment, followed by final wash, another, because highly sophisticated, and so that very cleaning should be preferred. And then embedding in resins. There is resins embedding. Material is embedded, but it will gradually infiltrate with still unpolarized resin. Little pieces of the resin infiltrated material and placed in the small holder. Then trimming of the resin block and ultra thin sectioning. After tipping, sectioning. And sections with a thickness about 17 nanometer are cut with special knives, claved glasses, and collection of, this is the sample like this. This only kept inside the TEM machine. So this is the TEM working principle, as similar, more or less same. The electron source consists of cathode and anode. Cathode tungsten filaments emits electrons. When heated, negative confines, cap confines the loosely focused beam. The beam is then accelerated. So here the electron gun and acceleration takes place, and this also it is inside the vacuum. And then electron beam is slightly focused using electromagnetic lens and lens apertures. The second stage and third stage platform equipped. Like that stage, and finally equipped with mechanical arm and holding a specimen and counting its position. So more or less you might be studying the welding also, plasma arc welding, laser arc welding, same concept of principle. The electron beams are coming and functioning in the under, and then TEM analysis can be taken out. Samples of the microscope range. Say these are yeast cells or fungi. That is a microorganism, fungus kingdom. That is the fungus material, a member of fungus. That is a TEM image like this, SEM image like this, Easter. These three images comparative. Here microscope image, TEM image, SEM. This is E. coli bacteria. That is a micro. This is one type of bacteria for that is bacteria. Yeah, one type of bacteria for food from the animal. It is coming. That is image different shapes. This also gel-like fluid. Gel-like fluid for the human. It is also some fluids, biological fluid. Generate most of the chemical energy needed to power cell biochemical reactions. Some of the TEM image of this bio products. Same image, blood cell image. Here the specimen generally known as fruits. There is a inserts are there. That details, that magnification. This one, each one, this one, minute body varying shape and structure. So this one for my research, nano composites samples are given. So just samples I have shown a lot of things. It took some imagination. Atomic force already explained, but it was how the cantilever tip is there, and it will shake based on that shaking, and it is focused on the laser beam. So AFM 3D, 2D image, atomic force microscope, 5 by 5, the 5, it will be 5 by 50 division, 50/50, that is 5 height, it will range the 3D image, single line, the 3D image will be show you. AFM, atomic, the TEM analysis. These things are from my research samples I added. Then microscope is over, then smart material. Smart material already you might be come across a lot of times, even though just recalling the first recorded observation, smart material transformation was made gold cadmium 1932 and 1938 brass copper, 1962 nickel titanium, like that development, and finally shape memory effect was found. So the nitinol is the final they have found in the laboratory, and based on that the gold cadmium and then copper 1938, and then for the nickel titanium, how the transformation, phase transformation, martensite, and then the heating it will austenite, again cooling martensite again. So heating, cooling, it will change in shape. So similar way, heat recovery, nitinol, only the copper based alloy came close challenging nitinol. After the copper based nitinol came, and during 90 and 1890, nitty material is very famous and increasing number of products. So nitty material is the finally came as a smart material. In that cold martensite, heat recovery, austenite, cooling, cold martensite, deform, same. So the material will undergo by external parameter, temperature or pressure or variations. So transformation mechanism, how it is happening. The austenite high temperature phase of martensite low temperature phase. So austenite is here acting as a high temperature phase, martensite acting as a low temperature phase. Two different forms of martensite material. That is a two different forms. These two are martensite. One is twinned and detwinned. This is austenite. At certain temperature, smart material will stay at thermodynamically stable. Sometimes it is stable at thermodynamic. Due to the transformation of mechanism, smart material have many special properties: shape memory effect and superelasticity. How the shape memory effect and superelasticity will be working. See that this is austenite, this is martensite. Martensite have a two category, twinned and by the application of stress and temperature, external stresses, forces, it will vary like this. How this, when the smart material twinned, martensite phase undergoes external stress. So when it is a twinned stage, external stress is applied. It transforms to detuned. So it will twinned to detuned, the external stress. There is no temperature change during this. So only stress variation, it is changing. And when the detuned material undergoes increase in temperature, the detuned material is transformed to austenite. So this will change again. The external stress is there, then again temperature change. This will detune to austenite. So similar way, again procedure, austenite will go back to tuned material when temperature goes down. So this tuned to detuned stress, detuned to austenite, temperature increase, again temperature decrease, like that. So like that, the temperature, there is a 4 characteristic temperature points: procedure 1, procedure 2, procedure what is explained. Martensite finished temperature, martensite start temperature, austenite start and austenite finished temperature. There is a graph. This is procedure as already explained. The procedure 1 and 2, the procedure 1 as a stress, it will come. Procedure 2, austenite form, again martensite. So the smart material experiencing external stress, changing temperature, increase and decrease. Finally, it will go back original tuned state. Because this procedure 3, recovery procedure from austenite to tuned martensite, will generate considerable force. This particular property can be in many ways. This is civil engineering structural applications. This is shape memory alloys, civil bridges. This is the application. Superelasticity, same thing will be acting as a superelasticity. Superelasticity, see, when is the detwinned is considered, then it is shape memory alloys. You forget about this one. Only these two interaction acting as a superelasticity. So this one, superelasticity, another important property, smart material. When austenite finish temperature AF at relatively very low, the superelastic material will stay as austenite under room temperature. So austenite, after finishing, it will stay as austenite. In this austenite phase, superelastic material can transform to detwinned martensite under stress. So here austenite and this austenite and detwinned martensite. In between these two, transition takes place due to the stress and the temperature. Then the superelasticity character will form. That is why here it is called martensite finish, martensite start, austenite finish, austenite, the ranges with respect to temperature and stress. Stress and temperature as the main factor here. There is no time like that, pressure or these two parameters. So it will impact formation of the superelasticity. So same thing is explained here. This one for shape memory, this one for superelasticity. shape memory, strain stress relationship, and this is super elasticity, strain stress relationship. Smart material. So we will see smart material. There is a main impact is stimuli. Stimuli means we will see a lot of stimuli. The temperature, pressure, chemical parameter, environmental parameter. These are stimuli. Like pressure, electric flow, magnetic flow, light mechanical. These are the stimulation to make simulate from original to another shape, again back to original shape. This is the smart material. So smart material means react to change their environment. That is, smart material can respond to heat, light, moisture, electric, magnetic field. The smart materials can be grouped by the color changing material, light emitting material, moving material, temperature changing material, thickness changing material. Like that, smart material can be. How it is? Smart structure may have sensor, nervous, actuator, muscles, and the control brain. So these three are the important. Thus, the term biomimetic is associated with the smart structure. The degree of smartness is measured in terms of their responsiveness. So how much it is responsive? That is the important parameter here. To environmental stimuli and their agility. The responsiveness implies a large amplitude change, while agility implies fast response. So see, the amplitude and the fast response are main things for the change of smart material, phase transformation. Their classification based on the relationship between the stimulus and stimulus means temperature, pressure, chemical parameter things, and response means how it is fast acting. These are the stimulus: strain, stress, temperature, chemical, pH value, electric field, magnetic, hydrostatic, radiation. Like this, these are. There is a application: aerospace, damage reduction, vibration control, shape control, adaptive. Disadvantage also there. Relatively expensive manufacturing machine. Most smart material have poor fitting properties, so it will undergo when loading, twisting or bending. Steel components survive 100% more than ordinary smart material. That is the drawback. Properties: sensing materials, actuation materials and devices, control the devices techniques, self-deduction, self-diagnostic, self-corrective, self-control, self-healing, shock absorber, damage arrest. So classification of smart material: piezoelectric, electrorestrictive, magnetorestrictive, thermoelectric, shape memory alloys, photochromic, thermochromics. These are the classifications. This how the input, this is stimulation, deformation. Output is potential difference, and potential difference will make deformation. Magnetic field will make deformation. Temperature will make potential difference. Temperature will make deformation. Like this, these are simulation, these are the output. These three are important components of the smart material: control, actuation, sensor component. So components data. See, this is the aim of the components: collect the required data. First, input raw data is needed by fiber optic sensing cable. That is the input, and after that, the data is transmission. It is collecting and then transmission. The purpose of the part is to forward and data RAM to local central command control transmission, and then after reaching the control area, command and control unit brain will actuate. The role of this unit is manage and control whole system by conclusion, determining this data collection, this is transportation, and this is the command starting what has to do next. The data instruction, motor nervous. This function of this part is to transmit decision and associate instruction back to the member of the structure. That is data motor further acceleration. Action device. Finally, purpose, and the muscles will implement the actions. Samples of the sensor, nervous. First is raw material, nervous. Second stage. Samples are diagrammatic way it is shown. If these are the components. Effect of some paper referred. The paper name is given, and what they are telling, the polymer component KN and NTK composite, lead, piezoelectric, ceramic. This is when ordinary, this is lipid, lithium is doped in KN is a polymeric elemental component, composite component. It is lithium is added. There is only lithium is there. There is a number of whites, and this is added with the lead-free piezoelectric element. This is the one chemical, that is a polymeric chemical composite element. KN and NTK composite lead-free piezoelectric is added with the lithium doped, there is a number of void is less. There is a difference. The paper is explaining one part. So on pure lithium is added, there is voids. Added with the dielectric, piezoelectric is the smart material types. Piezoelectric is the smart material type. So when it's smart material is added, the number of void is less. They are explaining that void is approximately 10 meter up here lip in and ceramics. Such voids are rare in image of composite ceramics. By comparing this image, the NTK becomes clear, namely composite lead-free piezo. So from that paper, it was taken. Same another paper referred this NN plate, that is NN template. There are a lot of methods are there to manufacturing the composites of using shape memory alloy. The one-time method is NN method. That is some chemical expansion. I think I forgot, but template method is there. Using that, they have taken XRT pattern and same image and scanning, that is same base, same only, same and TEM analysis. And they are from this, the improvement, there is a property improved by adding smart material with the composites using this NN template method. Same thing they are explaining, the structure depend number of size distribution template orientation. From the paper, it was explained, various images are shown. You can see NN template possesses single phase work structure, microstructure, average 15 mm and 5 mm width, 1 mm thickness. Thus, the templates can be mechanically oriented and applied shear force given. This is a procedure for application. Final result will be they are saying that the SCDs means selected area diffraction, electron diffraction for individual template reveals. This is the procedure they are doing. And finally, properties improved. That's all. This paper explained. Using addition of some smart material over the polymer composite, the property is improved. That is the net result. Here, same shape memory alloy. This SMP indicates shape memory polymer urethane. Samples, just diagrammatic way they are explained. Block dots, net points, block dots, blue dots, that is low mobility, red lines, high mobility. So when the blue dots, low mobility, red lines, high mobility. How the change, the SMU means smart memory polyurethane, SMPU, chains below transition temperature, low mobility. Again heating, it comes high mobility, red lines. Again further deformation, red lines. Again cooling under stress, again low mobility. Triggering high mobility. So changing temperature will change the movement of atoms in the some smart material. Example, it's also taken some paper, some sample was taken only, some part only it was taken, not fully paper. One of the diagram was taken and it was explained. And let us see this smart video is visible, or sir?
Yeah, yes, sir.
It's
yes,
visible
sir.
now, sir.
Visible, sir. Visible, sir.
Actually, audio is not clear, so that you can explain it now.
Huh?
Audio is not audible, sir, actually.
Audio is,
Ah,
the audio is there. Full audio is there.
I think you have to enable when you share it.
Now, oh, okay, sir.
No, still, we can't hear. Actually, when you share
Sir,
the slide, when you share the slide, so you have to enable the check marks. Then only it will be audible.
sir, what, sir? Continue.
Audio is
Audible,
not.
sir.
No, it's not audible, sir. Audio.
Ah, but full sound is there.
I
Huh?
don't know. I don't know whether we have
Oh,
to check the settings and all.
okay, okay, sir. Okay, we'll make it faster.
Okay, sir.
Yes.
Okay.
So this exam for the it's also same. We'll make it fast. Time there. It's the same retinal change. So the same two videos explains about the internal how the shape memory based on the temperature changes simulation back to original position. So these are the classification under this piezoelectric material. This is examples of natural piezoelectric material, and piezoelectric material, that is a variation change in electric charge. Based on that, the shape is changing, and voltage application, this change is mechanical change in the undergoes, vice versa. Some of the natural piezoelectric material, topaz, salt, sugar cane, DNA, enamel, dental enamels also comes under. And this one, yeah, back to it. So back to. Sorry, the time is there. Okay, I will go in this same only. This one, electrostatic material. It is also one of the smart material types. Material has same property as piezoelectric, but mechanically changes proportional to the square of the electric field. So based on electric field, so you might be seen in the ordinary this metal bottle. Some of the electric static. Normally you might be checked in any places also. So when it is revolving, this is combined due to electrostatic force developed in the material, and it can go along with this. And examples of rheological material. This is also one type of smart material. Is the science that concerned with the flow of liquids and deformation of solids. So that is rheology indicates liquid. The liquid phase can change through the application of electric or magnetic charge. This application fluid application brakes, shock absorber, damper, vehicle seats application. So it will liquid, it will act as a cushioning effect. So for example, practical example, food, biofluids, personal care products, pharmaceutical is shown. For food, ice cream like this chocolate, biofluid, blood like that, split machines, the personal products, nail polish, shampoo, that is also comes under this cadre. Like that, examples are there. Magnetostable materials by a magnetic field, using magnetic field, direct or converse will undergo induced mechanical strain. It acts as sensor and actuator. Example of when a magnetic field is applied, is compressing, acting, and vibrating automatically taking place by the application of magnetic force. So these are the classification. Further, thermo-responsive material. It is the ability of material change in properties response based on the temperature change. You might be seen in the cereal also some water coffee cup. When coffee is poured, it is visible. Thermal act is smart material. It's electrochemical material. It is also ability of material change is optical properties, color change when the voltage is applied across. LCD and cathodes are lithium batteries. Examples. Smart materials that they have made based on biomimetic material. These are biomimetic based on biological samples. Kingfisher has designed this Japanese bull. Not Kingfisher is the name of the bird, but the origin template they have taken like this. Velcro from burr, naturally smart material is available. Based on that, they have designed. This is the biometric material, as this slide shows. Example, biomaterial structure involved natural system and have a capability to sense the environment, process the data, and respond instantly. These are the biomaterials. It's naturally, it is automatic based on the temperature, it will react. Fluorines is the especially gauged molecules with the carbon atoms at the corner of the polyhedral. Structure consists of pentagon, hexagon, and there is a these are usually used in polymetric matrices for the smart systems, right? And smart gels, fluorines, gels also one type of smart material, and smart gel are that can stick or swallow by tablets are smart material. Inside the tablets, tablet including that cover we are swallowing, and it will be observed. That is, some of these can also be programmed to absorb and release fluids, respond to the chemical physical simulations. So it will react accordingly. The same thing is memory analysis explained here. And the shape, this martensite, deforming martensite, deformed martens, austenite martens. This also already explained some first day experts explained this. How the marks and this only we have seen in the structure based. This one 1 minute video, I think. Video audio is available or same thing, I think. Yeah, how the smart material changes original shapes.
Dhandapani sir, can we
Sir,
continue for 5 more minutes, sir?
Sir?
How much time we want, sir? Further?
10 slides, we'll make it fast.
Okay, sir. Okay, sir. Okay, sir.
So applications, aircraft, orthopedic surgery, dental, robotics, reducing vibration. These are the applications. Metrics, demerits, merits, simplicity, compactness, safety. Demerits are there, more expensive, low energy, complex control, limited bandwidth. And these are the nanomaterials also comes one way it comes under a smart material, and these there are elements. How the simulation elements like this nanomaterials elements samples are shown. Then how stuff is getting smarter. These samples for the smart material samples, and this how it is working stuff. We might not release it, but smart materials are starting make real. The kettles that change color when they boil. This change based on the temperature. Kettles, garments that plug into MP3. So in this they have MP3 is added in the garments. Player, batteries that report conditions. So the battery will say their maintenance condition is reflected in the attached. So these are the examples of smart materials. Smart material react environmental. The smart plastics do all sort of cool stuff. Polycarbolactone is a type of smart plastic used in making models. So models are making using this. Let us see this molding plastics and this completing complex assets and for making handles, grips, jewelries, and intricate shapes like this. Viscoelastic polymer also the example for the instantly becomes rubber impact and bounces it like ball. So soft moldable plastic. So thermochromic material, pigments change color changing material. Pigments change back to their original color when they cool. When they can be used to paints to create images that change, they get hot. So thermochromic ink can be printed on the range of materials such as plastic and paper. Thermochromic films or sheets, they have been printed with thermochromic ink. You can see these thermochromic materials. 2D heat sensitive temperatures ranges. The hand smart ink change color with the temperature color, and this interesting gimmicks they also kept in like this. Changes color when food is the spoon color will change depending on the temperature of the food for the feeding of the child. And here you see that useful marking material. Cold when his coffee is there, and hot when it changes the color. And photochromic material change color in response to light. Based on the light, photochromic pigments change color reversibly. Let us see the diagrams. Lenses become darker with increased sunlight, ultraviolet sunlight. See that, and the glasses change transparent to level of light, saving energy. The mini rainbow car, rainbow paint use rainbow effect in the bright sunlight. The car will show this during sunlight like this. Color changing wrist burn indicate when the sun cream needs to be reapplied when or more movement in the shade. So these are the change in color. Fluorescent pigments. Phosphorescent pigments store light and slowly release it glow in the dark color. So it will absorb energy and it will release it in the dark daytime. Fluorescent pigments really bright because they reflect of lots of light as well as reflecting visible light and absorb ultraviolet light. So extra visible light is, so these are the examples. So nanotechnology examples, Okay, that's all. Final application base. 1 minute video. It's a combination of piezoelectric and magnetic electric combined. How they are using it useful way. Megawatts, they are generating power. Okay, sir. Reference. Reference, sir.
Okay.
Thank you, sir.
Thank you very much, sir. Thank you, sir. Thank you, sir.
Okay, sir. Thank you.
Um, Thank you very much for your spending time with us for the past 1.5 hour, more than 1.5 hour. Um, Dr. Dandapani sir is also our board of studies member for our autonomous institution. Thank you very much, sir. Thank you very much. Very kind of you, sir.
Thank you.
I request our participant interact with our guest if you are having any queries, specific queries about smart materials and their applications. Or else you have to post the queries in your chat box.
Anybody? What is that there, sir?
Oh, okay, sir. I think no one having any queries. If you having any specific queries, please kindly unmute yourself and then and ask your queries or questions to our expert member. Sir, okay, sir. Thank you, sir. Thank you.
Okay, sir.
Can we wind up, sir? If some queries are there, I will contact you, sir.
Yeah, sir.
So,
You can send. No problem, sir. No problem.
okay, sir.
So,
Thank you.
and
Thank
also,
you very much.
I will say thanks to the principal and our HOD, Shanmugha Sundaram, and the coordinators for giving me opportunity to deliver this type of AICTE. I am very happy to. It's one of the opportunity for me. Thank you very much, one and all the teams. Thank you and all the participants also for the patiently listening. Thank you, one and all for all. Thank you, sir.
Thank you, sir. Thank you, sir. So today night I will share you one Google form, sir, for remuneration purpose and also the PPT. You are posting your PPTs there. Okay.
Okay. I will send you, sir.
Okay. Thank you very much, sir. Thank you, sir.
Thank you, sir. Thank you.
Thank you,
Thank
sir.
you. Thanks.
Participants, thank you. Thanks for your patient listening. We will wind up the section on today. Day 2 section was over. And we will meet you on tomorrow, 10 o'clock. Kindly join us on tomorrow's section, first section. Happy day. Thank you. Thank you very much. Kindly fill up your feedback form for all the sections, all the 3 sections. Mr. Balakrishnan sir is calculating your attendance daily basis. If you have any further queries or any clarification regarding your um, attendance, kindly contact our assistant professor, Mr. Balakrishnan sir. Thank you, Sudhakar sir, for your valuable feedback.
Dear participants, actually, I have sent a feedback link for session 3. Suppose if you found any error to upload your feedback, please contact me through WhatsApp number. I have posted my WhatsApp number in our chat box.
Balakrishnan sir, kindly stop the link, sir. The right
Okay, sir.
YouTube.